Question 1A
Yes.
is, what does a generator do?
Okay, what does a generator do?
Converts mechanical energy to electrical energy.
Right. 1. Generators. Convert mechanical energy into electrical energy.
Mr. Goodman,
Yeah.
I'm pretty sure it's recording audio, but it might not be.
So anyway, what does a generator do? It converts mechanical energy into electrical energy. Now, can you picture, remember we had the cranker, and I cranked the handle, and it made the light bulb light up?
Yeah.
That's a generator. You crank it. That's the mechanical energy turning into electrical energy. What's the other question?
What does a motor do?
Okay, what does a motor do?
Electrical energy to mechanical energy.
Right, the exact opposite. Convert electrical energy into, mechanical energy. So what do we mean by that? What's making the motor run?
Electrical energy.
Yeah, where's that coming from?
Maybe a direct source like a battery.
Yeah, probably a battery. If you had a battery in the circuit that could generate, put out the electricity to make something move. Yes.
I was thinking, I searched up yesterday. There were two types of motors: AC motors, which are alternating current motors, and DC motors, which we were talking about direct current motors.
Yeah.
Oh, what is an alternating current that makes?
Okay. Let's do a couple of diagrams, and we're
Okay.
going to get to that.
Gotcha.
Okay. Alternating current means the current goes back and forth.
Oh, okay.
Direct current, if you just have a battery hooked
It's
up
just
to a
one
light
line,
bulb,
yeah.
that's direct current.
Gotcha.
And we'll see a little bit of that. Mostly everything that we're going to talk about will be direct current. Shouldn't really say that. We're going to see some AC stuff. All right. So what's the next thing we have to talk about?
As shown below, a vertical wire L equals 0.3 meters is moving to the right at V equals 10 meters per second in a magnetic field of 2.5 T as indicated.
Is that X's or dots?
6 axis,
X's.
and the resistance is 5 ohms.
What does X's mean?
Into
Going away, right?
the page.
Okay. I gave you a model to work with. A dot is the tip of the arrow coming at you. X's are the tail feathers of the arrow that you would see going away from you. Can we all remember that?
Mm-hmm.
Okay? So, X's are into the board. Okay, now aren't there some rails, metal rails that go like this?
Uh-huh.
Those metal rails are conductors, and this wire can move along it, right? Now, is there a resistor over here?
Yes.
Yeah, 10 ohms.
So this is...
Diagram says 5.
It's 5 ohms. The diagram says 5 ohms, Mr. Goodman, and the problem itself said 10. So I worked with 5.
I apologize. We'll work with 5 ohms then. Those things happen. And believe me, I would never take points off if something like that happened and you didn't know which to use. Okay, so this is not the first introduction to magnetism. We've been talking about magnetism. I think what I better do is quickly show you something with a charged particle in motion. There's 2 right-hand rules. The one I want to use right now is the right-hand rule that will show us the direction of the force acting on the charged particle as it moves through a magnetic field. The rule is this. Put your thumb in the direction of positive motion. Put your fingers in the direction of the B field. That's a flat hand. Open those fingers up. And the fingers go into the board, thumb that way. Where's the force? Up, that way. The B stands for magnetic force, okay? B stands for magnetic field. So B here was how many Tesla?
It was 2.5, sorry. 2.5 Tesla.
2.5 Tesla. Okay. So, as we saw in previous examples, this is going to start to curve. If the thing moves sideways and there's a force this way, it's going to curve. Very much like in projectile motion, if I throw something sideways and gravity pulls it down, it starts to curve. Well, this is a little bit more extreme because that force is going to keep turning as well instead of just going in one direction. So it's going to make it go in a circle. You can look that up in previous problems that we have done. So what do we have over here? Do we have positive particles in a wire? are the positive particles moving to the right? Well, then there's going to be a magnetic force on it, right? Which way? Up. Will the particles move in a circle? What do you think? They moved in a circle here. They're not going to move in a circle here. How come? Where are the wires located? I mean, where? I gave it away. Where are the positive charges located? In a wire. If the wire is moving this way, those particles aren't going to go in a circle. They're just going to start moving up. Does that make sense? They're confined to the wire. Now, when I talk about the positive particles moving, do we know what particles really are mobile in a metal wire? The electrons. And historically, nobody really knew the difference between the positives and the negatives, which ones were moving. It turns out that it's the negatives that are moving, but negatives would be moving down. And that's the same thing as talking about the positives moving up, as we've seen in previous examples. So we're talking about positive motion. Even though they didn't know that it was the negatives that were moving, you still get the same results. Positives are going to move up. That means this end of the wire becomes positive, that end of the wire becomes negative. This can act like the battery then, generating electricity. It can generate a voltage. As the wire moves this way, it's going to cause a positive to be placed on that end of the resistor and a negative to be placed on that end of the resistor, and the positives will now flow through the resistor. Does that make sense? Well, that resistor could be a light bulb, right? So we could light up something with it. So give me the next question.
Oh, the next question was what direction is the force? And then after that,
Good, force is up.
find E along the vertical wire.
Well, what do we mean by E? Does anybody know the basic definition of E? We're going to make a formula list, and you guys are going to start like memorizing these things.
F over Q.
Right, F over Q. You don't want to be like searching around for that during a quiz. You're just going to have to know that the force per charge is the E. Have we ever seen in gravitation? Like, let me erase this and I'll show you what I mean. Here is a positive charge. Here is a little test charge. That could produce a field line in this direction. And they're going to come out in all directions. Is that right? Yes? The electrostatic field is the force acting on that little charge divided by that little Q. Okay? Very similar to, say, we had a large mass here and a little test mass. Then the arrows would be going in for gravity. Is that right? And so the gravitational field would be the force pulling on that little mass. And that would be G, the strength of the gravitational field. So we've seen these parallels last year in honors physics. This is something that we did, back in class. So in any case, now we have a new way of looking at the electric field. The electric field could be generated by moving through a magnetic field. This force would go up here, the magnetic force. You would divide by that test charge, and you would get an electric field along this wire. Does anybody know the basic formula for the magnetic force? Starts with a Q. Next is a V. QVB, hooray. We should give out stuffed animals. QVB over Q. Do you remember playing with QVB? We need to practice. QVB over Q. Hey, guess what? What is the electric field? VB. However fast this wire is moving, times the strength of the magnetic field, you will get an electric induced, we call it an induced electric field in this direction. So what's the answer? Take 2.5 times 10, and what do we get for answer?
25.
We get 25. And what do you think the units would be for that? Yeah, newtons per coulomb work fine. Could it also be meters per second times Tesla? Yeah, doesn't matter. Okay, tell me what the next question is.
Find the induced EMF or voltage from the
Yeah.
bottom end of the wire to the top end.
How many of you guys have heard of something called an EMF? Did we ever talk about that yet?
Yeah.
Okay. It stands for electromotive force. But it's not a force. This is another one of those historical artifacts that seem to linger. So, electromotive force. But it's not a force. What is it? A voltage. Isn't that interesting? But electromotive force, does that give you the impression that something's pushing this way? That's the idea. And if you take, well, how do you take the electric field and turn it into a voltage? Does anybody remember that? This is also going back to the honor system stuff. Who remembers the basic definition of voltage? Does anybody remember? Yeah, that was for Ohm's law. But before we did Ohm's law, there was even something more fundamental about what voltage meant. It's before that. This is going back last year. How about, if I write this, you're going to say, oh, yeah, I know. How about work per charge?
Oh, okay.
See that? Yeah, I hear the crowd moaning. Could we also think of it as a potential energy per charge?
Yes.
Yeah. So, like I say, you plug something into the wall outlet, and you get charges out of it, right? Who knows what the voltage is on a wall outlet?
Oh, I have that.
Yes, I suggested that maybe you start to remember these things, right? Common knowledge. I'll give you a hint. It starts with a one digit and one.
120.
Right, 120 volts. So let's just say we had an outlet of 120 volts. If we had an outlet with 120 volts and I plugged something into it, if I got out 1 coulomb of charge, how much energy would be coming out? 120 joules. So this is, I'm just trying to get you to think about numbers that maybe will help you solidify all of this. Could you take your Q, this is a common thing that people do, take the Q times the voltage, and you're going to get out the potential energy. Once it comes out, though, and it does something, then you could think of it as work being done. The potential energy would be converted into work. Does that make sense to you? Okay. So now, look at this formula for voltage. What is the basic definition of work? Thank you. Force times a distance, right? Divided by a Q. You know what? I'm not going to call it a D. I'm going to call it an L, okay? I'm going to call it an L. It's a distance. Can somebody figure out how to get the electric field in here? F over Q equals E. So that means the voltage is E times an L. Can you picture that? We'll talk more about that, whether we're gaining voltage or losing voltage. But right now, I want you to take a look at that formula and come back over here. The voltage is the electromotive force. So that's going to be E times L. So electromotive force, E times L.
7.5 volts.
Do we know what the E is?
Yes.
25 newtons per coulomb.
I'm sorry, 7.5.
So times 0.3 meters. Is that right? So that's going to be 7.5 volts. Is that right?
Mm-hmm.
So let me just throw it right here. 25 newtons per coulomb times 0.3 meters is 7.5 volts. That means this generator is going to generate 7.5 volts. If I took a voltmeter and I hooked it up here, you're familiar with our voltmeters, right? We've used them. That voltmeter would read 7.5 volts. That's also going to appear over here. We're going to have 7.5 volts going across the resistor. Do we lose voltage along a wire that has no resistance? No. So if we're at 7.5 volts here, we're at 7.5 volts there. If we're at 0 volts here, we're going to be at 0 volts there. So now we have a voltage drop of 7.5 volts across the resistor. Tell me the next question.
What is, I think it's what is the current?
It's current.
I had a feeling. How do you calculate the current? Give me another formula for voltage.
A voltage equals current times resistance.
Yeah, V equals IR, and that's what we're going to use with the resistor. We know the resistance is what?
5 ohms.
5 ohms. Why did I put 10?
7.2.
5 ohms, and that's 7.5 volts. And the current will now be, divide by that, you get 1.5. 1.5, who knows the units?
Amps.
Amps. Okay, for the viewers on this video, we're over here. V equals IR, 7.5 volts, equals I times the 5 ohms, and 1.5 amps is the current.
What is the direction of the current through the vertical wire?
Through the vertical wire, the current would have to be up. And through the resistor, it's going to be down. We would say that the current is clockwise. So here we have those rails. Here is the resistor. And here is that vertical wire. Okay, now, let's see if I can get a marker with different color here. We had the positive charge in the wire moving that way with the velocity v. We had the direction of the B field was into the board, correct? Yes. I'm going to quickly review. I put my fingers in the direction of the B field, thumb in the direction of positive motion, and the force was this way, correct? Okay. Now, this gets tricky. If that's not tricky enough. Once the charge starts to move, we have another velocity, don't we? So I'm going to call this velocity 1 and force 1. This is how things get started. The wire is moving this way and the force is that way. That makes the charge start to move up. But now what's going to happen once the charge starts to move up? I'm going to put that charge up here. Can you picture this charge? Look, I'm going to use another color for the let's see, I'll use it again. We got a velocity now in that direction. Can you picture this being like a secondary motion?
Yes.
I put my fingers in the direction of the B field, my thumb in the direction of positive motion, and now there's going to be a magnetic force this way. It's not like there's this charge has this force on it and that charge has that force on it. They all have the same stuff. I'm just drawing them separately so we can see it happen. Does this make sense? So now, that force is going to make the wire slow down. Well, what do you think we're going to have to do if we don't want the wire to slow down?
Put another force on it.
I have to push on it. The only way that we can keep this wire moving is for me to push on it like that. Who do you think makes the light bulb light up? Do you think it's the magnetic field? No, it's going to be me. If I don't turn the cranker, if I don't push the wire, if I don't exert myself, the generator stops generating electricity. Okay? And that's the reason why it's going to stop generating electricity. Because as long as, if there's any current, it's going to cause the wire to slow down and come to a stop. Does this make sense? Okay. So, what's the next question?
What is the direction of the magnetic? Oh, hold on, I think I did that. What is the magnitude of this magnetic force acting on the vertical wire?
So we need to know that magnetic force, right? Well, there's a little bit of a trick to that. And I'm going to tell you that the magnetic force is equal to QVB. Okay? As far as we're concerned, this was something that was just discovered experimentally. There was no theory. People just say, okay, we did an experiment, we found out it works that way. Sometimes we like to put the little perpendicular sign there. What's that mean? The velocity has to be to the perpendicular to the B field. Look at it. Right-hand rule. When we go like that, you see how everything is at right angles.
Yeah.
I'm starting off with the velocity, and that's perpendicular to the B field. That is also perpendicular to both of those. Okay? All right. If you don't have a velocity that's perpendicular to the B field, you're going to have to. We didn't lose audio at home. We're just thinking.
Component.
Yes. You have to break it up into components, and you use the velocity that's perpendicular. Does that make sense? Okay. Here's a trick question for you. I'll get back to this in a second. Trick question. You have a magnetic field that looks like this. Not going in or out of the board, to the right. And you have a positive particle with a velocity like that. What will be the direction of the magnetic field force acting on this charged particle? Right, there isn't one. Try it. It won't work. Put your fingers in the direction of the magnetic field and your thumb in the direction of positive motion. There's nothing perpendicular to work with. You get it? It won't work. Okay. So we'll talk more about that another time. So now, we don't know how fast these charges are moving, do we? But we did calculate the current, didn't we? Who remembers what the current was?
1.5
1.5 amps. I don't have current here, do I? But I can do a trick and get current. What is the basic definition of a velocity? A distance over time. And we had the distance, didn't we, right? So I'm going to change that FB into Q times that length of wire divided by the time it would take that to go there. And now this is a beautiful little formula because the Q could be divided by the T, and that's...
That's charge per time, so it's amps.
Yep, there's your current. ILB. Can everybody remember that formula?
Yes.
You can derive it again. It's easy. But I just don't think you're going to want to keep deriving it every time you try to do something. ILB. What is the I?
1.5 amps.
1.5 amps. What's the L?
0.3 meters.
0.3 meters. What's the B?
2.5 Teslas.
2.5 Tesla. And what do we get for that magnetic force?
1.125 newtons.
Okay, so we have 1.125 newtons over here. How hard will I have to push now to maintain constant velocity? The same thing, 1.125 newtons. What if I pushed harder? What would happen? The wire will speed up. If the wire speeds up, what will happen to the light bulb? It'll get brighter because I'll be generating more current. Hey, if that happens, I have more current. I'm going to have more force going backwards. I have to push harder, won't I? It all makes sense, right? Okay, so now, next question has to do with perhaps power.
No.
It's asking
What keeps the wire moving?
Oh, okay, so what keeps the wire moving?
Your push.
That. Me pushing it forward. If I don't push, if I let go, it's going to slow down. Give me another
This
question.
one is, how much power is required to keep this wire moving?
Power. Who remembers the formula for power?
Per time.
What?
Work per time.
Work per time. Remember running up the stairs? Whether you're running up the stairs or pushing a wire at a certain speed with a force, it's a force times the distance divided by time. That's force times distance divided by time. What is distance over time? So we could just say force times velocity, couldn't we? How much force am I applying? 1.125 newtons. At what velocity? It's not up here, but we had it before. Was it 10 meters per second? It was? So then we're going to write 10 meters per second. And by golly, it's 11.25. I love units, especially at 9:36 in the morning.
Watts.
Watts. Who remembers watts? Right? Okay. So that is the power that I have to put into this device. Where do you think this power is going to? What are we doing with this circuit? What are we powering with this? Yeah, a resistor. Let's just say it's a light bulb. We're making the light bulb light up. Does anybody remember a formula for electrical power?
Amps times voltage.
What was it?
That was I times V.
Yeah, current times voltage. You want to check that out? Now that's a different V. That's a voltage. Okay.
Oh yeah, that's right.
Let's just see if we can make that work. Is it current charge per time? Yes. Isn't voltage work per charge? Yeah? Does anybody see it? Alex is going to see it. There he goes.
There we go.
So the Q's cancel out and you get work per time. So this is another formula you're going to want to remember. You're not going to want to have to fish around for it and go, oh my gosh. We're going to end up with quite a list of formulas, aren't we? I'm telling you, if you do 200 or 300 problems.
A day.
Yes, a day. It's going to still start to sink in, okay? All right. So what are we going to plug in for the current? We already figured that out.
Yeah, 1.5 amps.
1.5 amps.
Times 7.5.
And what did we say the voltage was across that resistor? 7.5 volts. Who can tell me what 1.5 times 7.5 is?
11.25.
All right, did you really just,
Yeah, I actually calculated.
you actually calculated?
Yeah, I actually calculated.
This is a major breakthrough in science, at least at room 265 this morning. What does this tell us?
It's the same.
They're the same. I put in this much power, the light bulb is consuming that power. Didn't I tell you? I'm the guy generating the electricity? Well, there's the numbers. They don't lie. Okay?
How does the power required to maintain the velocity of the wire compare to the power of the system?
Yeah, that's it. The powers are the same. That's the question
It's
is,
a motor.
so who's really making this thing run? Me. That's the point. Go ahead.
Is it a motor or a generator?
Okay, is it a motor or a generator?
Motor.
Did you say a motor?
Yeah, it's motor.
You're saying it's a motor?
No, I'm thinking.
Oh, you're pushing a generator? Okay.
Yeah.
Oops.
Yeah.
Oh, wait.
You know, it's so funny. You guys know what motors are.
Oh,
They run on
yeah,
batteries, right? You have to plug it into the wall, right? There is no plug here. There's no battery, okay? So you know what it is. The reason why I point that out is because I've been doing this for decades. When I give a quiz, the kids can do the hardest stuff, and then I ask an easy question, is it a motor or a generator, and they get it wrong. I don't know what happens. People do silly things, okay?
The diagram is changed by replacing the resistor with a 6-volt battery, as shown below. The vertical wire, L equals 0.2 meters, is initially at rest in a magnetic field of 1.5 T as indicated.
Is that dots or X's?
Axis.
X's?
Battery 6 volts.
Oh, I scrolled up too much. Assume
How
the
many?
1.5 Teslas.
1.5 Tesla. The voltage on
6
here
volts.
is 6 volts.
And resistance is 3 ohms.
Resistance is 3 ohms.
And there's a resistance. Did I actually draw a separate resistor?
I don't think so. I think
Sometimes I do, sometimes I
I think
don't.
you just said R equals 3
Okay,
ohms.
I gotta tell you something. In real life, there's always a resistance of some sort. And in fact, that resistance could very well be inside the battery. Have you ever heard about resistors inside the battery? Batteries have an internal resistance. The chemicals that push the charges through are also impeding the flow. It's not like there's no resistance at all to the flow of charges through the battery. So we'll talk more about that another time, but sometimes I actually put a resistor here to indicate that. And that resistance was how much?
3 ohms.
3 ohms. Okay. So can you picture this being the positive end of the battery, that being the negative end of the battery? And if you're not used to that, you'll read more about batteries in your chapter notes. So the voltage is gained through the battery in this direction. So if a charge flows into the battery, it will come out the other end with 6 joules of energy per coulomb that comes through. Does that make sense? So we got some energy. Now it's going to come through here, and now it's going to go through the wire like this and back around. That means we're going to have a positive charge flowing this way with a velocity now, won't we? Do you think we might be able to figure out a force?
So going down.
You're going to put your thumb in the direction of positive motion. You're going to put your fingers in the direction of the magnetic field. And now there's going to be a magnetic force in this direction. Does that make sense? Do we have to calculate the strength of that force? Probably. That's probably one of the questions, right?
Yeah, A is the direction. Oh,
Okay, we got the
No,
direction.
A is the direction of the current through the vertical wire.
Yeah, that's it, down,
Down,
right?
yeah.
Okay, and what else?
Find the magnetic force acting on the vertical wire.
So that's a magnetic force, and that would be QVV, right?
Oh,
Yes?
I skipped B.
What's B?
Is that for
Magnitude
the-
of the initial current.
That would be a good idea. Let's do the initial current. Can I go V equals IR? What is the voltage?
6 volts.
6 volts.
Resistance.
And then across that resistor is 3 ohms, right?
So 2 amps.
So we're going to go 6 volts current, 2 ohms. And we're going to have 2 amps, no, 3 amps, right? What am I
Yeah,
doing?
3, sorry.
3 ohms,
Yeah, 2
2 amps. So there we have our answer for the current. Okay, but I don't have current in this formula. If I don't have current, what was the little trick I showed you? What's the definition of speed?
It's distance over time.
Distance over time. That would be the length of this wire divided by the time. And what is the, what's the Q over T then?
Current.
Current. So what is it?
Times length times
ILB. You know, I called this a capital L, but usually we would write that as a lowercase l. There's reasons for that. We'll talk about something called inductance, which is a capital L. It can get confusing. So what do we have here for our I?
2 amps.
2 amps. What's the L?
0.2 meters.
0.2 meters. What's the B?
1.5 Teslas.
You're on top of this, dude. And what do we get?
0.6 newtons.
0.6 newtons. Now, you know I drew this force acting on a little charge, right? But the wire is packed with charges, and all of those forces added up together is 0.6 newtons. Okay? So we now know that the wire is going to start moving in that direction.
Wire begins to move due to its magnetic force. Which way will it move? Left or right?
Did you say left?
Right, so
Okay, right. It's going to move this way, won't it? Yes? So as this wire starts to move, won't we now have a second velocity to concern ourselves with? The first velocity was the current going down. So I'm going to call that a 1 and a 1. Guess what's coming up, kids?
another.
Another velocity. So I'm going to just put in another charge here and put in another velocity. That's a second velocity now. Because the wire is starting to move this way. If I do that, you getting good at this? There's going to be a magnetic force going up. This is tricky, isn't it? Don't you think that magnetic force is going to cause trouble? Which way is the battery trying to push these charges? In the wire, which way does that battery push the charges? I'm making multiple choice, up or down. That battery is going to push the charges in the wire down. That charge is moving because of the battery. Does that make sense? So that motion was caused by the battery. What will the motion through the magnetic field cause? A force in the opposite direction. Do you think that that is going to oppose the battery? Is this going to help generate more current? No. It's going to reduce the current coming from the battery. I need to know if I'm reaching anybody here. Something's not making sense. I see faces that concern me.
Yeah, can you say that again?
What I'm saying is as before the wire started to move, we could say that there was a current going this way, right? That current came from the battery, making this go down.
Oh, but the magnetic force.
But now, as this wire starts to move, this force is generated, and that's opposing what the battery's trying to
current
do.
will go down. Okay, that makes sense.
So will the current increase or
Or
decrease? It's going to have to decrease now, won't it? Right?
That makes sense.
The faster the wire moves, the bigger that force. The bigger that force, the more the current decreases. Eventually, this wire is going to go so fast that the current will be zero. When that happens, the wire can't go any faster.
Yeah, I got that right.
It can't go any faster. We call that terminal velocity. Thank you.
See, I got this right.
Does that work for you?
Yeah.
Okay. Well, anyway, let's continue on here. Does anybody know the formula for the magnetic force? Q, V, B. Doesn't that sound familiar?
Yep.
Right? Yes? And then, now, this is just because I've done these many times, I know what I want to do now. Could I take that force and divide by the Q and say E equals VB? So there's going to be an electric field the wrong way. Okay? And then that electric field, what if I multiplied it by the length? Does anybody know what I get when I take a voltage? And this is called an EMF in these types of problems. And that voltage is called a back EMF. Do you have any idea why they call it a back EMF? Because it's not going forward. It's going the wrong way. It's preventing the current from flowing. Does that make sense? Okay. So this back EMF could eventually be how big?
Infinite?
Nope. What's making the
6
wire
volts.
move?
Oh.
What?
6 volts?
6 volts.
Oh,
What's
okay.
making the wire move is the battery.
Yeah, yeah.
So this wire will only go as fast as that battery will allow, and that's going to be limited by the voltage. So we're going to have here a back EMF. As this thing gets bigger and bigger, it's eventually going to equal the 6 volts. And at that point, no more current will flow. So the wire is going to reach terminal velocity. So let's write up here 6 volts equals VBL. We don't know what that velocity is, but when that is 6 volts, we call that a terminal velocity. Do you see I put the little T there?
Oh, okay.
Terminal velocity. What's the B field?
1.5 Tesla.
1.5 Tesla. What's the length?
0.2 meters.
0.2 meters.
We got 20
And what do
meters.
we get for what do we get for a terminal velocity?
20 meters per second.
Okay, 20 meters per second for a terminal velocity. At terminal velocity, what's our current? Once we reach terminal velocity, you have any idea what my current would be?
Yeah, 2 amps.
Try again.
0.
0.
Oh, okay, sorry.
Because when I'm at terminal velocity, the voltage going backwards is equal to the voltage going forwards.
Okay. So the current
Boom,
cancel.
nothing's happening.
Gotcha.
I think this is very interesting.
This is.
Now I'm going to tell you a little story. Day before yesterday, I was using my electric drill. I was drilling holes in blocks of wood so I can screw them to the base of the benches that we're building for the nature trail.
We're building benches.
Yeah. If you want to go out, in a little while I'll take you out there. I got some stuff to do. So I'll go out and I'll show you what I'm up to. My wife was using the shovel and killing poison ivy. Now, the poison ivy, stuff grew in. But in any case, the drill got caught and the stopped turning. All of a sudden, the indicator came on that it was overheating, and it stopped working. It's a thermally protected drill. Why would it overheat if it stopped moving? Isn't the drill running on a motor? What's this?
Motor.
A motor. The electricity makes this thing move, and it could very well be turned into a drill. Okay? So what would happen if I grabbed the wire and stopped it from moving? There would be a tremendous amount of waste heat. What would happen to my back EMF if I stopped it from moving? It'll be 0. If I stop this thing from moving, then there won't be any velocity to generate this back force. You get it? So if I stop the drill from moving, there won't be a back EMF, and I will be at maximum current. The current initially was 2 amps, right? Imagine if that resistance was like 1 ohm. My current would be 6 amps. What if my resistance, maybe my drill has got very low resistance when it's not under load, okay? Maybe it's 0.1 ohm. I could end up with a lot of current, couldn't I? Can you picture that? So in a lot of motors, if you prevent them from moving, you're not going to have any back EMF. You're going to get a surge of current. And then that can burn out the motor, because too much current makes for a lot of heat. Even if you have little resistance, you can generate a lot of heat with more current. Did you like that story? How many of you have ever plugged in a vacuum cleaner, turned it on, and the lights in the room dimmed for a moment? Before the motor starts to turn, just when you turn it on, will you have a lot of current or low current the moment you turn the switch on? A lot of current. Because you don't have any velocity yet. That's what's happening in your vacuum. You turn it on and there's a surge of current. Well, if the current is going into the vacuum cleaner, there won't be as much left over to go through the lights. Does that make sense? You're going to get a voltage drop in the circuitry in that room. So what I'm trying to get across now is that, yes, the stuff we're talking about isn't just for AP exams or SAT tests. It happens in our daily lives. It just happens all the time. Okay? So what questions did I miss? So due to the motion of the wire, the magnetic force is now
Oh, sorry. No.
due to this velocity itself. Right?
Okay.
Now wait a second. Let's make sure we answer the right question. What if I said, what is the magnetic force acting on the wire due to the current in the wire? What would be the answer? To the right. What is the direction of the magnetic force due to the motion of the wire to the right? That would be up. I'm not, trying to sugarcoat this. This is hard, okay? Do you think this is harder than a lot of stuff you've done so far in physics? There's multiple steps to all of this stuff, and it's all in 3D. I will warn you about magnetism. There is no way we can just say, oh, you can do it in 2 dimensions. We did that like projectile motion in 2 dimensions, didn't we, right? If we wanted to make it simpler, we would have been talking about motion in 1 dimension. I can't reduce the dimensions in magnetism. You got to use the right-hand rule, which is automatically 3D. Okay? Go ahead, give me another question. Okay? That force is going to decrease the current. And, is there another question?
No.
As the velocity increases, the current will decrease. Until if we reach terminal velocity, no current.